Hello, good evening. I would like to apologize because I can't attend in person, and thank you for the conference organizers that understand my case. So I need to present online. My presentation will be talk about the using a quantum node connected via a quantum cloud to perform IoT quantum network. And let's start with our main topics, which is talk at the first about the quantum communication principle, quantum communication limitations, solution and possibilities, and related work, and our suggested model about the quantum nodes connected via cloud to the quantum computer, which will work as server. Let's start with the comparison between the classical and the quantum computers. Classical computers, as we all know, that it is used the binary bit, which is must be on, that represent the logic 1, or off, that represented by logic 0. And this is a series of these binary bit will represent the information that used to in the classical computer. While in the quantum computers, we are using something that completely different, which is called the qubits. These qubits have a special properties. This first property is superposition, that meaning that the quantum computer could represent the state at 1 and 0 on the same time, and this will give a high power for the quantum computer. And the second thing, important property, which is used and give the power for the quantum information, which is the entanglement. Entanglement actually is a work such as a magic connection between two qubits, if even if they are distinct and travel for long distances. According to the above, the superposition property giving the power to the quantum computer because it is the basic for the quantum register. Let's explain. Uh, if we have one qubit, we will represent two states on the same time. If we have two qubits, we can represent four qubits on the same time. If we have three qubits, we will can represent eight states on the same time, and so on. This is which gives the power for the quantum computer over the classical one, and which make it more useful if we use it on the data center, on the servers, instead of or integrated with the classical computer. But there is still many limitations for use of the quantum system. We say previously that we have entanglement and superposition for the quantum bits, but here these quantum bit properties are fragile and attenuated if they are travel for the long distances, and there is a loss of coherence between these two qubits. Decoherence is the losses of the coherence, and the coherence which give the qubit the power of superposition. Due to this decoherence, the qubits are extremely fragile, so that their ability to stay in superposition and entangled state is attenuated. Another limitation, which is represent power and limitation on the same time, is no cloning theorem. The no cloning theorem, meaning that the state is impossible to create an independent and identical copy of an arbitrary unknown state. It is represent the power in the side that our information cannot be stolen by eavesdroppers, and on the same time we cannot transmit the information for long distances because we cannot use a repeater to copy and forward it. But there is a solution. Um, Bridgel and Door on the late of 19th century decade suggests a new quantum repeater that will work on the has the similar job of the classical one, which is transmit the information for long distances, but its principle of work is different completely. Quantum repeaters are based on two quantum principles, which is entanglement swapping and Bell pair. And based on these two properties, he is will solve the coherence, attenuation, and qubit fragility. And the quantum Bell pairs will generated between two neighboring repeaters, and entanglement swapping will connect distance repeaters with each other by connecting their Bell pairs, and at the end we can connect two two distance nodes by using a quantum repeaters. Related work, actually there is very too much novelties and contribution in the field of quantum information, but here we will illustrate only something that are related to my work and suggestion. First, we talk about the quantum repeaters type. Actually, at the 2016, I'm sorry, Jonas suggest three type of quantum repeater node. First one is called meet in the middle, which is contain this BSA. BSA is abbreviation for Bell State Analyzer. This Bell state put in the between two quantum nodes. Both quantum node will send photon, and this BSA will create entanglement and share for the both these nodes. The problem with this BSA is situation due to geographical area, and it must be there is a synchronization between sender and the receiver, and it must know the number there's time, buffer size, and others. It has many advantage and disadvantage, and it is used according to the situation. The second one is sender receiver type, which is have only built one built on BSA node, which is put it in the receiver. The sender will send the photon, and on BSA create the entangled pair and share it to the sender. The third one, which is midpoint source, in this type needed for the entangled photon pair source, EPS, in the middle, and each node must have a BSA node. This node in the middle will create the entangled photon and share for both sender and receiver. In our work, we will use the first one. Second related work is the second novelty is for Deelberg and his group, her group from Netherlands. They are suggested a link layer protocol and simulated. This is by using a few qubits executed on supercomputer. The third suggestion, which is the third contribution is for Takako Matasio from Japan, who is suggest a rule set that coordinates the operation of a quantum network over both link layer and network layer. Based on the all the above, we suggest our model. We connect, just connecting different nodes via a classical channel and a quantum channel to a quantum computer. This quantum computer will as well as a server or database, such as this computer connected to multi things. This quantum computer could process, storage, work as processor, storage memory. This has different advantages. One of these advantages is to save information securely, as we know, because most important use for the quantum communication is the security and the high power processing. This quantum computer could work separately or integrated with a classical computer to connect these terminal nodes via cloud to it to collect information, process it, and forward it to the connected node via a classical channel. The processing will work as in details here. A quantum node activated classically by sending a boot up notification to the BSA node. BSA node we explained in the previous section. And BSA node will calculate the photon emission time per stride for all neighboring quantum node and photon detector for recovery time. This BSA forwarded this information classically for all neighboring nodes to generate entanglement. At the end, the quantum node notified BSA node classically that he is the work was success or failure, and then the BSA node will close the communication and notify for a new round trip time. This is the BSA node, which is put in the middle between two quantum nodes, or which is sender and receiver. The receiver in our case is a database. The point in the middle will create entangled pair and share for both nodes. Then after the shared entangled pair sent, the sender sent its information to the receiver, and on the receiver side, the quantum computer receives the information, process it, and return the instruction. When the sender received the instruction, sent a new request to establish a new communication. This is in the future will be applied using a simulation thanks to Takaki Matasio, who is built a QISB a quantum simulation package on the ONNET++, which will be able us to generate build a quantum network without need to the real quantum computer and calculate the fidelity of the network and other quantum properties. Thank you for your listening.
Okay, so thank you for the presentation. We have time for questions or
Okay.
comments. So it seems there are no questions. So let's thank the speaker.
Thank you very much for your listening and goodbye.